Okay, I guess. Shall we begin? So welcome everyone to another TCS Plus talk. We're very excited to have Bill Kuszmaul today, who'll be talking about linear probing revisited. And just before we begin, I do want to encourage everyone to keep their cameras on to give Bill some sort of visual feedback. And I will be recording this talk and putting it up on YouTube. If you have any questions, feel free to unmute yourself and ask it, or I'll also be monitoring the chat. And just before we begin, I do want to advertise we have a talk, I believe, either next week or in 2 weeks. Guy Blanc will talk about decision trees. So without further ado, Bill, please, the floor is all yours.
Great, thanks a lot. And thanks everyone for coming today. So yeah, I'm Bill Kuszmaul. I'm a fourth-year PhD student at MIT. And the work that I'm going to be talking about today is joint work with Michael Bender at Stony Brook University and Bradley Kuszmaul at Google Cloud. So this is based on a paper that's upcoming at Fox. And the point of this talk is really just to revisit kind of what's one of the oldest and most widely taught data structures in computer science, the linear probing hash table. And the talk's going to have 3 parts. So first, we're just going to review the classical results. What's a linear probing hash table? How does it work? What's the guarantees? But then I'm going to show you some new results that suggest that actually linear probing hash tables behave very differently from how we've classically thought about them. And then in the third part of the talk, I'll show you some of the analysis for why this happens the way it does. So let's start by talking about classical linear probing. A linear probing hash table is a data structure that stores elements in an array, and it supports 3 operations. So it supports insertions, deletions, and queries. And insertions are super simple to perform. What you do is if you want to insert some element x into your hash table, well, first you compute a hash of x, h of x for some hash function that we'll assume for now is just fully random. And this takes you to some random position in your hash table. And then what you do is you scan forward until you find a free slot where you can place your element. That's how you do an insertion. So queries are also simple, and they work essentially the same way. If you want to find out whether some element x is in your hash table, well, you just hash the element, and you walk forward until either you find the element that you're looking for, meaning it is in your hash table, or until you find a free slot, meaning the element isn't there. And then the final data structure that a hash table has to, the final operation that a hash table has to support is the deletion. And deletions are actually a bit more subtle. So it turns out there's several ways you can implement deletions in a linear probing hash table. But the most classical one, and the one we're going to be using today, and we'll see that this is actually an important distinction, is to use what are known as tombstones. So that means that when you delete an element, all you do is you go and you find that element, and you mark it as deleted. And that marked element is called a tombstone. And what's interesting about tombstones is they actually interact differently with insertions and queries. So if an insertion comes across a tombstone, the insertion can actually remove that tombstone and put in the element being inserted in its place. So tombstones are essentially free slots from the perspective of an insertion. Queries, on the other hand, when they come across a tombstone, they have to be much more careful, because the element that you're looking for might actually be to the right of the tombstone. So queries can't treat tombstones like free slots. Queries can't just stop when they encounter a tombstone. They have to basically treat it like an element. And so because queries treat tombstones like elements, that means the last thing you have to do, there's kind of one more thing you have to know if you're going to implement a linear probing hash table, which is that you don't want your tombstones to overaccumulate too much. And so every so often, in order to avoid overaccumulation, you should rebuild your hash table from scratch and clear out the tombstones. But it turns out that doesn't really change the average running times of any of your operations. And if you do everything right, you can have all three operations interact together kind of harmoniously. So that's the classic linear probing hash table. And it's an old data structure. So it was invented in 1954 at IBM. And one of the things that's interesting is that, almost 6 decades later, it's still one of the most widely used hash tables designs in production. And that's because there's a whole bunch of things that are nice about linear probing. So it's a relatively simple data structure. It avoids the overhead of storing pointers. So it's more space efficient than, say, chained hashing. But the thing that really makes linear probing special, and the thing that gives it its competitive edge still today compared to other hash tables, is that it has just phenomenal data locality. And what that means is that each operation accesses only one small contiguous region of memory. So in 1954, what that meant is that on the IBM 701 machine, a given operation might be able to get away with accessing only a single drum track on the machine. And since accessing drum tracks takes a lot of time, that was a big win from an engineering perspective. But if you fast forward today, what data locality means is you might be able to get away with accessing only a single cache line on a modern machine. And since accessing cache lines takes a lot of time, again, that's a big engineering win. So linear probing has this great thing going for it, which is it has just great data locality. On the other hand, linear probing also kind of famously comes with a corresponding set of bad news. And to see that, all you have to do is analyze how much time a given insertion takes. So suppose you start with an empty hash table, and you fill your hash table up to be a 1 minus 1 over x fraction full. So for example, if x equals 100, then this is a hash table that's 99% full. And actually, this parameter x is one that we're going to be using throughout the rest of the talk. So this is the one parameter that I want you to memorize. And we refer to this quantity 1 minus 1 over x as the load factor of the hash table. Okay, so you're at a load factor of 1 minus 1 over x, and you perform an insertion. How much time is that insertion going to take? Well, when a lot of students first learn about linear probing, their intuition is that this insertion should take time roughly x. And that's because 1 in x of the slots in your hash table are free. So it seems like if you look at roughly x positions, you should find a free slot. And in fact, this intuition was so strong that in the early work on linear probing in the 1950s, researchers went so far as to say that they were pretty sure that this must be what's going on. But it seems very hard to analyze. And in fact, if you graph it, it doesn't quite seem to fit. It seems like there's some engineering issues, but they're pretty sure that this is how you should think about linear probing. And 2 years later, in 1963, Donald Knuth came along, and he wrote this paper that just completely blew everyone's minds. And this was actually Knuth's first paper on the analysis of algorithms. So it's kind of a historically important paper. And Knuth was, in some ways, the tone that he took in the paper was almost kind of bashful. He's saying, I'm almost kind of embarrassed to be writing a paper about such a simple problem, but I feel like I have to clear the record. Because it turns out the expected time of your insertion isn't order x, it's actually quadratically larger. It's actually order x squared. And in fact, he figured out the more precise what the constants were and everything, and it was a beautiful paper. And the phenomenon that Knuth had discovered is something we now call primary clustering. And all this means is that as you put elements into your linear probing hash table, they have this tendency to cluster together into runs that are longer than you might expect. And so the way that textbooks have historically described this phenomenon is they said, well, it's kind of a winner keeps winning effect. So the longer that a run gets, the more likely it is to accrue additional elements, which causes kind of a positive feedback loop. It turns out that's not really the whole story. So in particular, if that's all that was going on, then primary clustering would actually only have a constant factor effect on performance. And Knuth pointed this out in his early work. He pointed out that actually the much more important aspect of the phenomenon is this globbing together thing that occurs. And what I mean by that is that a single insertion might increase the length of a run, not just by one, but it might actually connect together two runs. So a single insertion could dramatically increase the length of the run containing it, and that's what causes this quadratic blowup to occur. And the result is that for any given element, the expected length of the run containing that element is actually pretty large. It's actually quadratic. Okay, so there's one more thing that you should know about primary clustering before we've kind of covered the classical results. And that's that primary clustering is actually really a phenomenon about insertions. It turns out there's a simple trick you can use to completely avoid the effects of primary clustering for queries. And this trick was kind of described by Knuth and Amble in 1974. And the idea is that you just modify your hash table so that within each run of the hash table, you store your elements in sorted order of their hash. So for example, if you have a run containing elements with hashes 5, 5, 6, and 6, you store them in this order. And you have to modify how you implement your data structure a little to do this, to maintain this invariant, but it's pretty straightforward. So what you do is when you're doing an insertion, first you find the place where the insertion wants to go, and then you find the next free slot or tombstone after that, and you slide everything over by one, so that you can make room for the insertion and use the free slot or tombstone that you found. And so it's easy to maintain this invariant in your hash table. And what it means for queries is that they don't actually have to go to the end of the run. So for example, if you're querying something that has a hash of 5, then as soon as you encounter an element that has a hash of 6 or larger, you can stop your query. You're positive that the element you're looking for isn't to the right of where you are. And this means that even though the expected length of the run that you're in is quadratic, the expected time taken by the query is linear. So primary clustering is really a phenomenon about insertions. And so now at this point, we kind of have the situation that we've been in for the past 5 to 6 decades, which is that linear probing is this very natural kind of terrific data structure. It has great data locality, and the queries are pretty fast. If you're at a load factor of 1 minus 1 over x, the query time is order x. But insertions are just problematically slow. They take quadratic time in x. And so the classic lesson from this, the lesson that's been taught in courses and in textbooks, is that you shouldn't use linear probing if you're going to be operating at a high load factor, if you care about space efficiency. And so what you use, well, there's lots of differing advice on this, but the common advice is that if you care about space efficiency and you also care about data locality, you should use what's known as quadratic probing. And what quadratic probing offers is it reduces the amount of clustering, but it comes at a cost, which is you also compromise on data locality. And the consensus view has been that that's just the way things are. If you want to get rid of the thing that makes linear probing bad, that is the clustering, you have to modify it so that you also compromise the thing that makes it so great, which is the data locality. So that's kind of the situation that we've been in. And this brings me to the second part of the talk, where I want to tell you about some recent results that I think really have the potential to change our perspective on this. And in particular, I want to show you that we can actually get rid of primary clustering. And not only that, but there's actually a real sense in which primary clustering is already gone, and it's kind of something we've just missed. So let me show you what I mean. So first of all, I'm not claiming that the classical analysis is wrong. the classical analysis is right, but its scope is a little bit more restricted than you might first imagine. So in particular, the classical analysis is considering an insertion-only workload. So you start with an empty hash table, you fill it up to be a 1 minus 1 over x fraction full. But in some sense, that's not the problematic case, because yes, the final insertion is going to be slow in expectation, but the vast majority of your insertions were performed at much lower load factors. And so actually the amortized cost of all your insertions is only order x per insertion. The much more concerning case, and the reason I think that linear probing is taught as this thing you shouldn't use at high load factors, is what happens if you fill your hash table up to 1 minus 1 over x full, but then you stay there. So for example, maybe you alternate between insertions and deletions. Well, then now all of your insertions are being performed in this very full hash table. And conventional wisdom has it that this means that all of your insertions should be suffering from primary clustering. They should each take expected time x squared. And there are versions of linear probing where that's the case, where it's just kind of point blank the case, where these two workloads can be analyzed in exactly the same way. But what I want to point out is that in the most classical version of linear probing, the one in which you use tombstones, the one we've been talking about today, this conventional wisdom isn't actually directly implied by the classical analysis. And that's because when you perform deletions, you put tombstones into the hash table. And at least in principle, those tombstones could actually change the combinatorial structure of your hash table and possibly change the average running times of operations. So at first glance, this may sound kind of pedantic, but I want to show you why this is actually an important point. It's because tombstones actually have, it turns out, this kind of anti-clustering effect. So insertions, you'll remember, have this tendency to glob runs together, while tombstones kind of have the tendency to break them apart. From the perspective of future insertions, when I put a tombstone into a run, I've basically split that run in half so that a future insertion can stop at this tombstone instead of going to the end of the run. And so this has this anti-clustering effect. And what's surprising is it turns out this anti-clustering effect isn't just a small thing. What I'll show you in a second is that this actually has a huge asymptotic effect on the expected time of future insertions. So the tombstones that we're putting in now from our deletions will actually significantly accelerate future insertions. And we can capture this with the following theorem. And this is the main theorem that I want to tell you about today, is suppose you have a linear probing hash table and consider any sequence of operations where the only restriction is you never fill your hash table to be more than a 1 minus 1 over x fraction full. But you are, for example, allowed to hover at 1 minus 1 over x full if you want. You can perform all your operations in the super full hash table. Then it turns out no matter what your sequence of operations is, there's no sequence of operations that actually gets hit very hard by primary clustering. In fact, your amortized cost per operation is always soft O of x. So this means that tombstones, the effect that they're having is on sequences of operations that take place at high load factors, tombstones are actually almost entirely eliminating the effects of primary clustering. Now I say almost entirely because there is still this tilde here, which means that we're kind of ignoring polylogarithmic terms. And when we first proved this, we were kind of disappointed. We thought, gosh, surely the right answer is order x. And so it's just kind of a weakness of our mathematical ability. But what we eventually realized is that actually, no, there's something more interesting going on here, which is that there exist sequences of operations for which the average insertion time actually isn't order x. It's actually at least slightly larger. So we proved a lower bound of at least x square root log x. So this means that primary clustering is almost completely eliminated by the tombstones, but there's still some small sublinear effect there.
Hey, Bill? So is this lower bound against this specific algorithm of utilizing the tombstones in that way, or is it a general lower bound over amortized insertions and deletions?
That's a good question. So it's and it's a lower bound against this specific kind of classical linear probing, where you use tombstones in the classical way. So insertions treat them like free slots, queries treat them like elements. And it turns out we'll talk a little bit about, there are some implementation details that affect the bounds here. So we'll talk about those in a few slides. And in fact, we'll see that this lower bound doesn't hold in general for arbitrary linear probing like data structures later, because we'll actually see that there's a way to get around it. So that's a great question.
Okay, there's also another question in the chat from Samson, who's asking if there's a stronger lower bound in the case where the hashes should be sorted after insertions to support faster query times, as you mentioned.
Oh, that's a great question. So actually, one thing that I should have said more clearly is we're actually going to assume that version for this whole talk. So in order to make sure that queries are fast, we're going to assume the version of linear probing where you sort things by hashes. And so one implicit guarantee that we're going to offer with every data structure that we talk about is that the queries have the classical runtime. They all have time order X, where X is the current load factor parameter. And so, yeah, so in fact, this lower bound and all of our upper bounds are in that version of the problem. Cool. Yeah, so questions are very welcome. And I can even easily adjust the length of the talk if it turns out people have a lot of questions. So that's one of the nice things about, I guess, getting given non-recorded talk is getting to answer questions. Okay, so these are kind of neat theoretical results. And when we proved these, we started to wonder, well, is this kind of a theoretical nicety, or is this something that you would be able to see in a real hash table? And so what we did is we went and we built a hash table. And what this experiment does is it fills a hash table, a linear probing hash table, from empty up to 98% full. And then at that point, it starts to alternate insertion, deletion, insertion, deletion, insertion, deletion. And what we graphed was the average time taken by each insertion. And what you see is that as we're initially filling up the hash table, the insertion time just skyrockets. You get this quadratic blowup exactly like the classical analysis predicts. But then as soon as you start alternating insertions and deletions, the anti-clustering effect of tombstones kicks in almost immediately. So your time comes way back down. And what's kind of surprising here is that, yes, tombstones are having an anti-clustering effect. But remember, deletions and insertions are 1-for-1 here. So for every deletion that's causing anti-clustering, you've also got an insertion that should be causing more clustering. And so that would seem to suggest that maybe once you start alternating insertions and deletions, you'd expect to just plateau wherever you are. But that's not what's happening. So what's actually happening is the tombstones, their anti-clustering effect overwhelms the clustering effect of the insertions, and your performance actually comes back down to be near optimal. So when we saw this, I have to say we were really surprised. And partly that's because this is an effect that's happening in real hash tables. This is an effect that's been around for a long time, but as far as we can tell, it's kind of flown under the radar. So we haven't found it anywhere in either the theory or the applied literature. It seems to be kind of a novel phenomenon. Okay, so since we're talking about the practical side of things, let me just comment for a moment about what does this mean for practitioners? So of course, there's a lot to it, but the basic message is that, well, linear probing actually can be a lot faster than you might think. But the kind of the more nuanced message is that actually here's a guide for what the implementation details are that you should care about if you want your implementation of linear probing to be fast. So for example, I mentioned at the beginning of the talk that there's several different ways to implement deletions. And actually, a common advice is that you should try to avoid using tombstones, because in some ways, tombstones make things kind of messy. And what we're saying is, no, actually, tombstones are a force for good. They actually make your hash table significantly faster at high load factors. Another implementation detail is how often should you perform rebuilds? So remember that every so often you need to rebuild your hash table and clear out the tombstones. And the classical thing to do is to do that every roughly n over x operations. Turns out that's kind of in some ways the natural frequency to do it at. But again, if our insight is that tombstones are a force for good, then that suggests that maybe we should try to let tombstones hang around for a little while. That way they have an opportunity to be useful. And it turns out that's true. So actually, if you really want to get things to behave well, you should rebuild every roughly n operations. And then finally, as we talked about earlier, as mentioned by Samson's question, we should, if we care about queries, we should order our elements by hash. And that's been known since the 1970s. But the thing that's kind of surprising in some ways is that these really matter. So for example, suppose that you don't perform your rebuilds every order n operations, you perform them every order n over x operations. Then it turns out you don't get the ideal performance that we've been talking about. Instead, you actually end up getting a running time that's kind of geometrically in the middle of the two times we've seen so far. You end up getting roughly x to the 1.5 average insertion time. Okay, so there's a question. Do you see a similar effect of insertion time going down significantly if you start at different values, say 50%? Well, I guess there's several things that you might mean by that. So if you're operating at a low load factor, say a hash table that's 50% full, your performance is just terrific. Like you get all your operations are just incredibly fast. And so it becomes kind of a constant, kind of a challenge of balancing the constants. So you might be able to get a slight improvement by doing, you might see some slight change, but it's not going to be a very significant thing. On the other hand, kind of if you do eventually make it to a high load factor, no matter kind of what situation you started in, then you will see this effect if you start performing deletions and insertions. You'll see this effect where the tombstones speed up the insertions. So that's the first set of results I wanted to tell you about. And this got us thinking, well, this is pretty neat. But we started to wonder, well, maybe there's some way to really get the ideal performance. Maybe we can just somehow completely eliminate primary clustering. And it turns out you can. So we came up with a new version of linear probing that we call graveyard hashing. And graveyard hashing actually has the ideal guarantee. Every operation takes expected time order x. And here x is actually based on the current load factor at any given moment. So even as x changes dynamically, so do the expected times of your operations. And it turns out that the trick is actually to make use of the insight we already have, which is that if tombstones are a force for good, then let's treat them that way. So what we actually do is we artificially insert tombstones into our hash table that aren't created by deletions. And so by kind of prophylactically placing these tombstones into the table, we can speed up our insertions even in situations where there aren't enough deletions. So for example, even in an insertion-only workload. And this might sound kind of abstract, but actually here's a very concrete way that you can do this. So in classical linear probing, every order n over x operations, you rebuild the hash table and clear out the tombstones. Well, graveyard hashing does the same thing, except that in addition to clearing out the tombstones, you now place a bunch of new tombstones into your hash table, spread evenly across the hash table. And the idea is that you should make it so that the number of tombstones is roughly equal to the number of free slots in the hash table. Balance those out. And the idea is that these order n over x tombstones that you've just put into the hash table, they're what's going to make your insertion super fast for the next order n over x operations. And actually, that's the only modification to the data structure. So besides that, it's classical linear probing. Insertions, queries, and deletions work the same as always. The only difference is in the rebuilds. And it actually completely eliminates the asymptotic effects of primary clustering. So now all of your operations have the ideal cost. And one thing that I want to kind of point out is that this is kind of taking a different side of the coin than the first set of results.
Fazer o pedido a gente, todas as visitas para o verão têm que ser propostas até segunda-feira.
I think that was an accident. Junia and I muted you, but if you had a question, you can maybe unmute yourself again. Okay. Anyways, sorry about that.
No worries. So, oh yeah, so I just wanted to point out kind of like these two sets of results are kind of on different sides of the same coin. So one set of results is analyzing the classical data structure, the thing we actually use that's already out there in the wild. And it's saying this data structure actually behaves differently than our classical analysis might seem to suggest. And then the second set of results is saying, well, what could the future look like? What if we were willing to come up with a slightly new data structure? Well, then it turns out we can actually eliminate primary clustering while keeping everything we love about linear probing, namely the data locality. And one thing that's kind of obvious, but I think is still worth saying explicitly, is that actually, when you make your insertions faster, you also improve your data locality because you're accessing an even smaller region of memory than you would have otherwise. And you can formalize that by analyzing graveyard hashing in the external memory model, which is the model you use to capture things like cache misses or disk accesses or IOs. And what you find is that graveyard hashing is actually optimal in the sense that if your block size, capital B, is at least slightly larger than your load factor parameter X, then the average number of IOs or cache misses or whatever that you incur per operation is actually 1 plus little o of 1. So this is kind of the best type of guarantee you could hope for. And what's interesting is that this is kind of the tightest version of this requirement you could hope for. In that, for example, if B was smaller than X, then in any given data block, you would expect there to be less than 1 free slot. So you couldn't possibly hope for your insertions to have this little 1 plus little of 1 guarantee. But we're saying that if B is slightly larger than X, then boom, you're in good shape. And this is an improvement over the previous state of the art, where Jensen and Pei had shown how to achieve a 1 plus little of 1 guarantee when B was omega of X squared. And by getting rid of primary clustering, that's what brings this X squared down to X. Okay, so that concludes the second part of the talk, where I kind of summarized the results I wanted to tell you about. And now in the third part of the talk, what I want to do is I want to actually tell you what's going on mathematically here. And we don't have time to kind of go through the whole analysis in detail, or even talk about kind of all the different parts of the analysis, but I can show you one kind of cute part of the analysis and explain how that gives some intuition for what's going on here. And to do that, let me focus on a simplified version of the problem. So we'll be focusing on the first result that we talked about, which is you've got this hash table that's a 1 minus 1 over x fraction full. And let's consider just a simple sequence of operations where you're just alternating. Random deletion, random insertion, random deletion, random insertion, etc. And let's just consider a sequence of n such operations where n is also the size of our hash table. Then let's try to understand why is this theorem is true. why is it that our amortized cost per operation isn't order x squared, but it's actually soft O of x? And to do this, what I'm going to do is first I'm going to tell you about kind of a seemingly unrelated combinatorial problem. And then we're going to tell you why that problem actually captures something important about what's going on with linear probing. And then we'll come back and I'll show you the solution to the problem. And hopefully that'll give you some insight into what's going on here. So the combinatorial problem is very simple. We have an x by x grid with x squared dots in it. And here x is actually the same parameter that we've been using all along. It's the load factor parameter. And let's assume that these dots are colored randomly, so that each dot is independently either blue or red with equal probability. That's the setup. And then let's consider some monotonic path through this grid, going from the bottom left corner up to the top right corner. And for any such path, we can talk about the surplus of the path, which is the number of blue dots under the path minus the number of red dots under the path. So it's the amount by which the blue dots under the path exceed the red dots. And the combinatorial question that we're interested in is if each dot is randomly blue or red, and if you look at all possible monotonic paths through this grid, what's the maximum surplus of any such path? Okay, so what does this have to do with linear probing? Well, the relationship is kind of fun, which is that, okay, we want to analyze these n insertions and deletions that are occurring. But rather than analyzing each insertion individually, we can take kind of the alternative perspective, which is let's draw a vertical line somewhere in our hash table. And let's ask the question, how many of the n insertions are going to cross this line in expectation? So how many are going to start to the left and finish to the right? And what you can show basically by just rearranging some sums is that asymptotically, this question is the same thing as asking what the average time is of an insertion. By the way, by finish to the right, I mean use a tombstone or a free slot to the right. So the insertion, you might actually place the element to the left, but how many insertions hash to the left of this line and use a tombstone or free slot to the right of this line? Okay, so this turns out to actually be equivalent to what we want to solve for. And then to analyze the number of insertions that cross the green line, you basically want to do the following thought exercise. We consider the roughly x squared positions to the left of this line. And I claim, at least intuitively, that you can just focus on the insertions and deletions that occur in these positions. So actually formalizing that takes some work, but the intuition is just that, well, we expect the lengths of in this hash to be roughly x squared. So these are the positions whose insertions and deletions are at risk of crossing this green line. And then if we focus just on the operations that take place in these x squared positions, it turns out what we should do is we should think of them as being plotted like this. We represent an insertion by a blue dot, we represent deletions with red dots, and we use the x-axis to indicate the position in the hash table where the element being inserted or deleted hashes to. And we use the y-axis to indicate the time at which the insertion or deletion occurs. So for example, this blue dot represents an insertion of an element that hashed to this position and that took place relatively late in the sequence of operations being performed. So we plot our insertions and our deletions. And then it turns out that if what we want to bound is the number of insertions that manage to cross this green line, it suffices to instead bound the maximum surplus of any monotonic path through this plot. And in fact, what's going on is that if we ignore the insertions and deletions that occur to the left of these positions. And if we assume that these positions are initially saturated, then actually these two quantities become equal. So the number of insertions that cross the green line becomes precisely the maximum surplus of any path. And the intuition here is that kind of the path with the biggest surplus represents the path through time and space in which the insertions have the biggest edge over the deletions. So the insertions manage to get by the tombstones created by the deletions and cross the green line. So that's the basic intuition. And by the way, I just want to mention the reason that we end up with x squared dots, roughly, is that we're considering x squared positions. And we expect there to be roughly 1 dot per position in this plot. So that's why our combinatorial problem ends up being on a grid with x squared dots in it. Okay, so that's the intuition. But now let's just focus on the basic combinatorial problem. So we'll push all the details aside and ask, what's the biggest surplus going to be of any monotonic path? And I claim that if your grid is an x by x grid, then the maximum surplus is actually going to be soft O of x with high probability in x. And to get some intuition for this, let's kind of imagine for a second that we just consider the path that goes all the way up and then all the way to the right. So it contains all the dots under it. What would be the surplus of that path? Well, you would have x squared dots under it. That would mean that the standard deviation for the number of blue dots under it and the standard deviation for the number of red dots under it would both be square root of x squared, so roughly x, which would mean that with constant probability, we expect this path to have a surplus of roughly x. We would be surprised if it had significantly larger surplus than that. Well, what this claim is saying is it's saying that actually that's representative. In fact, if you take the maximum over all paths, the surplus is only slightly larger than what you'd expect from any given path. And that's interesting because there's exponentially many paths here. There's roughly kind of, there's 2x choose x such paths. So you can't union bound over all of them. But nonetheless, this is claiming that kind of all of their surpluses are correlated enough that the maximum surplus isn't much better than kind of the 75th percentile surplus. Okay, so how can we prove this? Well, this is where we get to do kind of a fun combinatorial argument. Let's start by considering something simpler than paths, which are rectangles. And what makes rectangles simpler is that there's not that many of them. There's only, roughly x to the 4th rectangles in our entire grid. And so let's bound the surpluses of rectangles. If a rectangle has some perimeter r, well, that means it contains at most r squared dots. And so this is the same analysis we did before. R squared dots means the standard deviation on the number of blue and red dots is roughly r, which means you expect the surplus of this rectangle to be not much larger than r. And you can apply a Chernoff bound to conclude that it's at most order r log x with high probability in x. And we'll do a slight abuse of notation, and we'll just write that as soft O of r. And this is true with high probability in x. And there's not that many rectangles out there, so we can just union bound over all of them and say, actually, with high probability in x, all of the rectangles have this property. The perimeter of any given rectangle is roughly proportional to our upper bound on its surplus. And then we can use that to analyze the paths. So what we're going to do is we're going to decompose the area under the path into rectangles. And the way to do that is with the following recursive process. First, draw a rectangle from the middle of the path down to the bottom right corner. That splits the path into 2 pieces. And then recurse on those 2 pieces. So draw 2 more rectangles. and then keep recursing until your path has been entirely decomposed into rectangles. Now, what does this tell us about the surplus of the path? Well, the surplus of the path is just the sum of the surpluses of the rectangles. But remember that for each rectangle, the surplus of the rectangle is soft O of the perimeter of the rectangle. But we intentionally designed our rectangular decomposition so that the sum of the perimeters of the rectangles would be small. So in particular, any level of recursion, the sum of the rectangles at that level is total perimeter order X. And you can bound the number of levels of recursion by order log X. So the sum of the perimeters is guaranteed to be order X log X. But that means that the total surplus is soft O of X log X, which is soft O of X. And so that's a simple bound for the surplus problem that kind of explains why, even though there's so many different paths you could take through this rectangle, the red dots, which represent the tombstones, are always able to kind of tame the blue dots, which represent the insertions, and ensure that there's never too big of a surplus of insertions under any given path. So that's the path surplus problem and kind of the basic description of what it has to do with linear probing. And this problem really does capture what's combinatorially going on for how tombstones and insertions interact. So it's true that the full analysis is more involved, and connecting these two problems together properly ends up taking a lot of work. But nonetheless, this path surplus problem ends up being the key for both the upper and the lower bound for this problem. So for example, the task of proving that x square root log x lower bound that we saw earlier ends up reducing to the task of proving a lower bound for the path surplus problem, also of x root log x. And so it's kind of neat that this basic combinatorial problem ends up being what governs the behavior of how tombstones and insertions interact. So that concludes the third part of this talk. And kind of in summary, we revisited linear probing hash tables, which are this old and widely used data structures, but which come with this major drawback, which is primary clustering. And then we saw that actually, kind of surprisingly, primary clustering is not quite as scary a villain as it first looks. You can actually make it go away, and there's a sense in which it's already gone. And then finally, we looked a little bit at the combinatorics of what's going on here and why it is that tombstones have such a remarkable anti-clustering effect. And if you'd be interested in learning more about the paper, I'd be happy talking more about it after the talk or offline, or you can also read the preprint on arXiv. Thank you very much.
Thanks, Bill, for a wonderful talk. Yeah, we can open the floor up for a few questions, and eventually there are some questions now, or otherwise I can stop the recording and we can ask some questions offline as well. So actually, I had one question. Just from the plot that you had shown, it's kind of interesting that there, even after all the runs of insertions, there aren't any big spikes. Is there like a hope to kind of get not only an amortized result, but also like a worst case if there, I don't know, if there are no long runs of insertions or something along those lines? Oh, I think you're muted, Bill, by the way.
So I guess there's two. Let me just clarify the question. So is the question whether we could get like a worst case expected time bound or actually like a high probability worst case bound?
Good. I guess, yeah, unexpected worst case found.
Yeah, so that's an interesting point. That's an interesting question, and it is actually, I think there's interesting research to be done here, because one of the things about our analysis is that by virtue of analyzing we don't analyze insertions individually, right? We analyze kind of this proxy for insertion time, which is how many insertions cross this line. And that means that we're kind of missing out on things like, what's the tail distribution look like for insertion times? And it seems very natural to assume that if you have a good workload that's alternating insertion, deletion, you should have, and if you have fully random hash functions, you should have a terrific tail on your running time of operations, but you can't really extract that tail from this analysis. So figuring out what that tail is would be a pretty cool thing to do.
Okay, are there any further questions or? Well, let's thank Bill again. And I'll stop the recording.